Located in the city of Kobe, Japan's RIKEN Center for Computational Science is home to the supercomputer Fugaku. Since June 2020, Fugaku's superlative capabilities have earned it the top spot 4 times in a row in global supercomputer performance rankings. Moreover, Fugaku is user-friendly. Allowing fast results with popular research software, it's already being used by many scientific projects and companies. High-performance computing systems like Fugaku meet high expectations, adding value, leading to unexpected innovations, and transforming society. Research for global sustainable development goals is already underway, as is research for a Japanese initiative that provides high-tech solutions to society's problems for a more comfortable and more prosperous future, known as Society 5.0. Fugaku is already bringing results and driving innovation across a number of fields, helping scientists to create better climate models, forecast the impact of natural disasters, discover new drug compounds, and develop new materials. Let's look at how Fugaku makes these achievements possible with virtual digital twin versions of our world.
Inside the cells of the body, countless protein molecules swim around, surrounded by water and other molecules. Reproducing these microscopic movements in a virtualized environment helps us understand how these proteins function. But a single protein is made up of tens of thousands of atoms. Molecular dynamics simulations that can reproduce these complex interactions require a powerful supercomputer. Yuji Sugita is the leader of a RIKEN research team. They tried using Fugaku to run molecular dynamics simulations to investigate how the COVID-19 virus invades cells. Viruses cause disease by invading our cells and turning them into virus-reproducing factories. A virus has so-called spike protein projections on its surface that bind to receptors on the surface of the cell, gaining access inside. To get a closer look at this interaction, the team used Fugaku to run Genesis software, an application with a 10-year development history. In a short time, it allowed them to reproduce the activity at the tip of the spike protein in great detail. Next, they plan to investigate how changes there at the end of the spike protein allow the virus to bind to the receptors and gain access to the cell interior. They believe simulating the complex movements of proteins will help us better understand diseases and develop new drugs to fight them.
In early 2020, a new and unknown infectious disease struck the world, an invisible enemy forcing people to live as never before. That disease is now known as COVID-19. In response, Japan declared a first-ever state of emergency, urging people to stay home. Many companies also required employees to work from home. As the world searched for effective steps to limit the spread of the virus, a research team led by Makoto Tsubokura at RIKEN and Kobe University used the not yet officially operational Fugaku to run simulations of droplet and aerosol transmission. The results showed quantitatively for the first time that masks can be very effective as an infection control measure. Non-woven surgical masks were found to reduce the dispersion of droplets and aerosols by around 80%, performing well as filters. The team ran additional simulations showing that partitions and ventilation can reduce the risk of infection in office settings, and a combination of air conditioning and open windows can be effective in classrooms. Using Fugaku allowed them to simulate 2,000 different scenarios in a short time. Next, the team will study how this virus enters the body and how it attacks the immune system once it's inside. As we transition into the post-COVID era, they'll be working with a network of COVID-19 specialists they've met through this work.
As global tectonic plates move, they cause stress to build up in the Earth's crust. When that stress is suddenly released, an earthquake occurs, sending seismic waves through the ground up to the surface above. This can cause violent shaking that damages buildings and puts lives in danger. To mitigate that risk, a research team led by Professor Tsuyoshi Ichimura at the University of Tokyo's Earthquake Research Institute is simulating each phase of an earthquake event, including resulting building shaking. They gather all the relevant information from the crust layers below to the building structures above and create a virtual double. The simulated region is massive. It's an area 205 by 256 kilometers in size and 100 kilometers deep. The huge simulation clearly demonstrates Fugaku's outstanding capabilities. This shows a hypothetical earthquake directly under the greater Tokyo area. You can see the seismic waves rippling out across Japan's Kanto region. The challenge of this simulation lies also in its ultra-high resolution, with grid cells as small as 12.5 centimeters across. Let's look at an underground shopping arcade in the heart of the large city. We can see that some parts of the arcade shake more than others. This simulation can also visualize conditions at particular locations in the arcade. This exceptional modeling achieves both a massive scale and ultra-high resolution. With Fugaku's powerful supercomputing, they solved 1.2 trillion math problems based on learning from 20 trillion computed data points. Nevertheless, the team plans further improvements, using still more and better quality data, making the simulations even more realistic.
まだまだ世の中には使われていないデータがありますので、そのようなデータの利活用をさらに促進するようにシミュレーション手法の開発をしていきたいというふうに考えています。そして5から10年後の防災力の向上に資する基礎研究を実施したいというふうに考えています。
In meteorology, training refers to a series of storm clouds that advance along the same path, like a train. One after another, storm clouds pass or even stagnate over the same place for several hours, resulting in heavy rains and major flooding hazards. How these cloud trains form, however, isn't fully understood, so accurately predicting them requires additional research. A team led by Takemasa Miyoshi at RIKEN is working on making storm cloud training forecasts more reliable. They create a virtual model of weather conditions and then assimilate large amounts of real-world weather data into that model. Here's what they've learned. This map shows precipitation up to 1 hour after a train formation that brought heavy rainfall to southern Kumamoto Prefecture in July 2020. On first attempt, using the weather model alone, a train in southern Kumamoto isn't predicted, so this forecast isn't the best. But when they bring in vast amounts of data based on state-of-the-art weather radar stations across the island of Kyushu, a train in southern Kumamoto appears. This forecast is a great improvement. This shows that assimilating so-called big data can be very effective. The team plans to continue using Fugaku to carry out and validate computations for different weather conditions to improve forecasting and reduce the impact of natural disasters like flooding.
One project overseen by research team leader Takahito Nakajima at RIKEN is developing and commercializing a new class of compounds that can make solar cells dramatically more efficient. The new compounds feature a crystal structure known as a perovskite, which is quite different from conventional silicon materials. And with safety in mind, they're avoiding the use of lead. They're compiling a massive database with 10 million different possible materials and using Fugaku to perform an exhaustive search for the safest and most effective ones for solar cells. Another project, a collaboration between Nakajima and 4 other researchers, is looking for new photocatalysts that could be used to produce hydrogen. Hydrogen holds promise as a possible resource for next-generation clean energy, but it's expensive to make. So there's a need for photocatalysts that can produce large amounts of hydrogen at lower costs. The researchers are using the supercomputer Fugaku in an exhaustive search for photocatalysts with the potential for a major breakthrough. They might be able to increase the conversion efficiency from a few percent to over 10%, which would be a major step in making hydrogen more practical as a fuel. This approach is also being used to search for photocatalysts that might inactivate viruses.
A research team led by Professor Shinobu Yoshimura at the University of Tokyo is building virtual models of massive-scale clean energy systems. Their focus is on reproducing large generator facilities, such as furnaces that convert coal into a burnable gas for next-generation thermal power, and large offshore wind farms. These are complex simulations that integrate thermal, fluid, and solid dynamics. For the super simulations that take all these physical phenomena into account, the team is using Fugaku, augmented by artificial intelligence. Using data from laboratory test furnaces that stand a few meters tall, they've been able to faithfully recreate the conditions that occur inside coal gasification furnaces. Next, they're working to replicate those findings for even larger industrial test furnaces that stand tens of meters tall. They're also simulating exactly how air flows at large-scale offshore wind farms with multiple rows of turbines to gauge how turbine placement affects efficiency. These simulations are expected to quickly calculate on-site conditions for large wind farms. The ultimate goal is constructing massive wind farms in the waters around Japan, with dozens of turbines over 300 meters high. That's taller than the Tokyo Metro Government Tower.
カーボンニュートラル社会を実現する上で、巨大な洋上風車であるとか、巨大な次世代火力システムを使うということが重要なんですけれども、それを壊れないように、また所定の性能を発揮するように長期間使えるようにすることが大変重要だというふうに考えています。そのためにこのスーパーシミュレーションが大変大きな役割を発揮するというふうに考えています。
When designing large passenger ships and tankers, some up to several hundred meters in length, the fuel consumption and propulsion efficiency are critical factors. Conventionally, design of such large ships has relied on performance tests using scale models in large water tanks. This can be time-consuming and expensive. A team at the Shipbuilding Research Center of Japan, in collaboration with Professor Chisachi Kato at the University of Tokyo's Institute of Industrial Science, wants to replace the entire testing tank apparatus with a virtual one using numerical simulations. Their virtual water tank must faithfully reproduce the shape of the ship and, more importantly, the exact water flow around it. Beneath the rear of the ship, a rotating propeller pushes the ship forward. But the way the water flows into the propeller can significantly impact its efficiency. So for design purposes, it's crucial that the virtual water flows like the real thing. But complicating the design process along the hull of the ship, tiny swirling eddies, less than a millimeter in size, can form anywhere the hull surface meets the water. It's been practically impossible to reproduce these sub-millimeter eddies all along the hull of a large ship. With Fugaku, they're aiming for a virtual testing tank that faithfully recreates these tiny eddies, along with all the shapes of the ship's hull, propeller, and rudder.
Well, 単純に言えば一つは受験をするあるいは試験をするお金がいらなくなるということもありますし、それから試験の準備の時間もいらなくなると。ただもっと大きな目で言うと線形を設計したら、直ちにその線形に対する性能が評価できるので、そのものづくりのスピード自体を飛躍的に速くすることができるという点が一番大きなメリットと考えています。
The steps in the drug discovery process include identifying disease-related proteins and such, finding drug compound candidates that counteract those proteins, evaluating the efficacy and toxicity of the drug candidates, and conducting clinical trials to confirm that the drug candidates actually work safely in patients. Currently, AI and computer simulations are used separately in the steps of this process, limiting the overall efficiency of drug development. To address this issue, a RIKEN team led by Kyoto University professor Yasushi Okuno aims to build a new platform to digitally transform drug discovery. The new platform will make drug development hyper-efficient by integrating each step of the process through a combination of AI and computer simulations. It's a powerful approach made possible by the supercomputer Fugaku. Just recently getting underway, their work follows the steps of the drug development process. So, to begin, they're identifying disease-related proteins. This is based on the changes to gene networks that occur inside cells when a COVID-19 patient becomes severely ill. They're also looking for possible drug compounds effective against those disease-related proteins. Only with the power of Fugaku can they simulate and study how these compounds move through the cell on such a scale. This time, they were able to narrow 2,000 potential drug candidates down to around 20 in 10 calendar days. Going forward, they plan to incorporate AI into this simulation to identify possible drug compounds even faster. We often think of global economics as sourcing, manufacturing, distribution, retail, and consumption, distinct stages in a supply chain. But in reality, these stages strongly interact with one another. So when a pandemic or a natural disaster strikes, there's a significant risk of chain reactions that could halt economic activity. Moreover, it's difficult to calculate forecasts of how interruptions to the supply chain might spread because of the enormous amounts of data involved. With this in mind, a research group led by Professor Hiroyasu Inoue at the University of Hyogo used Fugaku to construct a large-scale virtual supply chain for Japanese companies. Each dot represents a Japanese company, and their goods and services flow from top to bottom, showing how the real-world supply chain branches out. Their analysis revealed that around half of these companies depend on so-called cyclical components. Take screws, for example. Screws are used to fasten parts. Those parts are used to build machines, and some of those machines are used to produce screws. A simulated shortage of cyclical components revealed subsequent downward trends in economic activity, often seen after a disaster occurs, second and third dips. This model also allows them to explore hypothetical economic situations. For example, if Japan had implemented as strict an initial COVID-19 lockdown as some other countries did in April 2020, the economic impact could have been around 4 times as severe. The team hopes to further improve the precision of this supply chain model and put it to use for economic forecasting.
今後はこのシミュレーションをより正確な方向に発展させていきたい。それにはデータを追加したり、モデルを大きくしたりということが必要です。そうすることであたかも天気予報のようにですね、明日の経済の予報のようなものができるというのが理想的です。
Fugaku is producing breakthrough results one after another. And the RIKEN Center for Computational Science is making Fugaku easier to use for even more people to use. For example, you can now run some of the same applications and software as Fugaku on cloud services. And the portal site lets you manage your Fugaku usage from a web browser. Using Fugaku is easier and friendlier than ever. We're also championing green IT. Fugaku is designed to be energy efficient as well as high performing, and we're always working to further improve that efficiency. Information technology evolves quickly. Amid global competition, the Center for Computational Science is already taking preliminary steps toward a Fugaku successor, a next-generation supercomputer currently known as Fugaku Next. We're also looking at ways to develop and integrate emerging computer technologies, such as quantum computing and artificial intelligence. As Fugaku evolves and its next-generation successor moves forward, the Center for Computational Science will continue to inspire science and technology breakthroughs and strengthen international competitiveness.